Let's examine permutations and combinations. Inside the boxes, I've listed all possible outcomes to the experiment of rolling a pair of six-sided dice. Let's look at permutations and Let's examine permutations and combinations and see what they can. Let's examine permutations and combinations and see what they can tell us about probability and statistics experiments. What I have in the chart below is the complete sample space for the rolling of a pair of six-sided dice. The column on the left represents the outcome of the first roll. The row on top represents the result of the second roll. And if we just pair them together, then we'll have an outcome for the entire experiment, which is a two-digit number. How many outcomes are there in this sample space? Well, there are 6 ways for the first roll to happen and 6 ways for the next roll to happen. That's 36 possibilities. But arranging them in this format is a lot quicker than drawing the entire tree. So, a distinguishable permutation is a unique way in which a set or number of objects can be ordered or arranged. In permutations, order matters. So let's assume that the result of 1, 6 is different from 6, 1. If order matters, how many different unique outcomes are possible? How many distinguishable permutations are listed above? I'm going to take a look at the chart closely. I see that 1, 1 has nothing like it. So it's a distinguishable permutation. But I also notice that 6, 1 is similar to 1, 6. However, because the order is different, these are distinguishable permutations. So the answer here is there's 36 distinguishable permutations. None of them is identical to another. Okay. It's interesting to note that the formula for this is just found by multiplying the different number of possibilities of the first roll times the number of possibilities for the second roll. That's how we get 36 distinguishable permutations. Now let's look at combinations. A combination is a unique selection of objects from a set or a number of objects. In combinations, though, order doesn't matter. Only the objects selected is what matters. So if order doesn't matter, then 1, 6 and 6, 1 would actually be considered the same combination. And what I want to do is I want to count up how many unique combinations we have here. So 1, 1 is the only outcome of its type. It involves 2 1s. So that's a unique combination. I would see that any other repetition here would also be a unique combination. So these will count as part of our unique combinations. What else would count? Okay, here's 2, 1. I haven't circled anything like it so far. I see that there's a 1 and a 2 up here, though. But those are the same combination because they involve the same objects in the same numbers. So for that same reason, 3, 2 here is going to be unique. 4 and 3 is unique. 5 and 4 and 6 and 5. So will these be, and so will these, and these. These are all unique combinations. The others that I haven't circled are actually just similar to ones that I have circled. Now let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. There's 21 unique combinations. Now, in this experiment, is this an example of something that would be considered with replacement or without? Well, I roll the die. It could come out of any number 1 through 6. When I go to roll that die again, do I take any of the numbers out of the mix? No. You can still get the numbers 1 through 6. So this would be with replacement.